Hi everyone and welcome to the Data Football Club. When analyzing a football game, specialists like to highlight amazing goals that were scored from unexpected positions. But is it possible to quantify at all the probability of a goal being scored? Well, over the past few years, a metric is being more and more widely used by football specialists, and this metric is called expected goals, or XG for short. In this video, I will explain the origin of XG, how to calculate them, and most importantly, how to use them correctly. In particular, we are going to build our very own XG model together. So let's get the ball rolling. Have you ever wondered how likely it was for an average football player to score from a certain position? Let's say, if they took a shot in the same situation multiple times, how many times would they be able to score? Once every 50 shots, maybe 100 shots, maybe 1,000 shots? Well, if we take the example of Juninho, which is one of the best, if not the best free kick scorer of all time. He managed to score multiple free kicks from crazy distances in official games, and it seems pretty fair to assume that this kind of performance is very unlikely to occur in most football games, wouldn't you say? But how unlikely? In 2012, during the MIT Sloan Sports Analytics Conference, a paper called An Expected Goals Model for Evaluating NHL Teams and Players by Brian McDonald was presented. This paper detailed a model which aims to predict goals from hockey game statistics. And one big particularity that football shares with hockey is that they are both low-scoring sports. This makes it harder to fairly analyze a player or team's performance only looking at their raw statistics. If we look only at the number of goals a player scored over a season, it might give us an incomplete view of their performance. For example, let's have a look at Robert Lewandowski's performance over the 2018-2019 Bundesliga season. Lewandowski scored 22 goals over the course of 33 games, of which he only missed 11 minutes. That seems like a good total for a striker, especially to the naked eye. If we stop there, it seems like Lewandowski performed fairly well, wouldn't you say? But let's go further. During those 33 games, he made 145 attempts. Considering he scored 22 goals out of the 145 attempts, that means he converted 15% of his chances. To give you an idea, this is relatively low considering that top strikers usually reach conversion rates of above 20%. But again, is it really enough to assess his scoring performances, you think? Do you notice there might be a bias in this analysis? Yes, that's it. We have no clue whether the attempts he took were genuinely hard or easy to score. It's not the same story if most attempts were taken from outside rather than inside the box. And that's where XGs come into play. An XG is the estimated probability of scoring a goal in a given context. And by context I mean the location on the pitch, whether it's a set piece or open play, and all the factors that are independent of the player's characteristics. According to the Understat XG model, during the 2018 to 2019 Bundesliga season, the sum of Lewandowski's XGs are 33.54. That means that we were expecting on average 11.54 more goals from his attempts, which would have brought him to a conversion rate of around 23%. And I just wanted to say that Lewandowski is of course one of the best strikers in the world, and that season Bayern Munich still won 3 titles. Nevertheless, the difference between his XGs and actual goals scored are very, very different to his other season, which might indicate a dip in performance in that year. A dip that he seemed to have easily overcome, as during last season he vastly overperformed compared to his XGs, and Munich fan can be very upset he wasn't there against PSG in the Champions League. There are many XG models out there, such as Opta, Understat or StradaBet. These models are obviously not open source, but however, some information on how they were built is publicly available. We know that Opta trained their model on 300,000 attempts with predictors such as the location on the shot, the body part used to shoot, and the type of assist. With this in mind, let's build our very own XG model. For that, we are going to need some data and some Python code. If you are no coder, don't worry, this is pretty simple to get hold of. And if you want to follow along with the code, the links are in the description below the video. The football events open dataset available on Kaggle gathers more than 900,000 events from around 9,000 football games from the top 5 European football leagues. Every row of this dataset is an event that happened in a football game. These events can be, for example, a foul, a substitution, or an attempt. Let's now define our modeling setting. We want to predict how likely it is for an attempt to result in a goal based on a set of features. In the football events dataset, we have the following relevant variables. Its goal, so whether it's a goal or not, the location, whether, for example, it's taken from inside or outside the box, the situation, whether it's open play or set piece, assist method, whether it's a pass or a cross, the body part, which is, I guess, self-explanatory, a fast break, whether it's a counter-attack. Therefore, our target variable is goal, and the remaining ones will be our features. IsGoal only takes two values, 0 and 1. This is known as a binary classification problem in data science and machine learning. Now that we know which features are available and which target variable we want to model, we need to choose a model or algorithm to learn the relationship between them. And one of the simplest yet efficient model in binary classification problems is logistic regression. Essentially, a logistic regression model can be written in the following way. Our target variable isGoal is assumed to be equal to a linear combination of our features and some remainder that is called a noise. This noise is assumed to be unpredictable. Thanks to the data collected, we have many examples of the pair features-target. The only unknowns in this model are the beta coefficients, which drive the magnitude of the impact of each feature on the target and the noise. Our purpose is to find the optimal set of parameters that minimize the noise with different techniques. Finally, to properly write the logistic regression model, we want our target variable to be between 0 and 1 in order to estimate the probability of scoring. We compose the right-hand side of our equation with a function called the sigmoid function, which takes any real number and outputs a value between 0 and 1. That way, we can ensure that all our predictions will be probabilities of scoring. You might say, why are we obtaining a probability of scoring when we're trying to model whether it's going to be a goal or non-goal? Well, this is the next step and final step, really. We are going to choose a cutoff value, and usually it's going to be 0.5. And if we have a probability of scoring that is above 0.5, we're going to assume it's a goal. And if it's a probability of scoring that's below 0.5, we're going to assume it's non-goal. That's in general for a binary classification problem. And I just want to say here that logistic regression is not an obscure model at all. It's not something that only statisticians use. It is omnipresent in our society. Take your emails, for example. When you open your mailbox and you see some of them categorized as spam, a logistic regression could be behind it. Using variables such as the format, the sender, the subject of the email, and the model will learn from a database of examples to correctly classify spam emails from actual emails. There are of course more elaborate models to do this task, but logistic regression has proven to be very efficient and, most importantly, very simple to interpret. As a little disclaimer to some of you data scientists out there, extensive work is obviously required to finally prepare the model, but for now, let's keep things simple and directly fit our logistic regression on all relevant data. To do so, we'll be using a little bit of Python code, and well, in Python vernacular, we load the logistic regression object class from scikit-learn and use the fit method on our dataset. And that's it. Our model is ready to be analyzed. The accuracy of our model is 90%. That means that it correctly classifies our data 9 times out of 10. However, even if it looks good, this might be a trap. A better way to assess the quality of a classification model is to look at its confusion matrix. Each cell of that table represents a number of observations that fits the categories specified in row and column. The first row gathers actual non-goals and the second row actual goals. The first column gathers predicted non-goals and the second column gathers predicted goals. If we look at the top left cell, that means that we have 202,228 observations that are actually missed attempts and predicted as such. That's very good, and we want as many observations on the diagonal as possible in general, and as few observations on the other two cells of the table. From this matrix, it seems like we do a great job at classifying non-goals as non-goals, but not such a great job at classifying goals as goals. That's definitely something we want to improve if we wanted to refine our model. Now that our model is trained and that we briefly assess its quality, let's see what it can tell us about our favorite football players. In practice, we don't really use the raw XG prediction, but rather the difference between XG and the actual number of goals scored. As in the Robert Lewandowski's example, this difference reflects whether the player is overperforming or underperforming compared to an average football player from the dataset we considered. We'll come back to that in a minute, but before, let's have a closer look at conversion rates. Over the course of the whole dataset, we have the following top 10 players in terms of conversion rates, with Bas Dost having the best conversion rates, 4 points above Lionel Messi. From 2011 to 2017, the time window of the dataset considered, Bas Dost played at SC Heerenveen in the Netherlands, Wolfsburg in Germany, and Sporting in Portugal. Therefore, only the 4 years he spent in Wolfsburg are part of our analysis. We can see he never played in a top 5 European club despite being the best player in terms of conversion rates over that period of time. And of course, there can be many reasons why this did not happen, but remember what I told you earlier. Conversion rates do not take into account the situation from which the attempts to score were taken. Now, let's look at expected goals. This tells a whole other story. Lionel Messi, with almost 58 goals more than what we were expecting over that period of time, that is around 25 more goals than that of Ibrahimovic, the second best on this list. It is not surprising for us football fans, but still, it highlights how exceptionally consistent Messi's goals are compared to the rest. We can finally put some quantitative analysis around that. And I don't want to end the whole Messi-Ronaldo debate, but you can have a look at Ronaldo's XGs there. And where is our dear friend Bas Dost here? Well, he got a very decent 26th place with around 12.5 more goals than what was expected, which is still a great performance, but not even close to Messi's. You might argue that you did not need XG to know that, and that's fair. However, it gives you a clear quantitative view of other less famous players as well. Any player that you run through that model will be evaluated in seconds, and this is a helpful tool for recruiters when buying players. As a conclusion, let's have a look at the limits of XGs, and in particular the ones of our model. An obvious one is that it only considers the shot, and not what led up to it. When Maradona, Son or Messi dribbled 5 or 6 players before scoring, they will certainly receive an XG close to 1, because when they shot, they were very close to the goalkeeper, sometimes even with an empty goal. But if we consider the whole sequence, what led up to the goal should probably be 0, because those are very, very exceptional goals. Another limit is the capacity of a player to create chances for himself, which is not evaluated in the XG metric. For example, Ousmane Dembélé, in the round of 8 of the Champions League against PSG, was heavily criticized for missing a lot of goals with potentially high XG. But looking only at XG does not evaluate his capacity to create those chances. Thirdly, and I think that's a very important point, we do not take into account the defender or the goalkeeper position in that model, which really can influence whether you're going to score a goal or not, because if the goalkeeper is really far away that way, and not at all in his goals, he can score a goal maybe from 30 meters, so that doesn't matter. But the reason why we didn't include that is because in the football events dataset on Kaggle we didn't have this information, of course, otherwise we would have put it in. And to end on a more mathematical note, statistical model assumptions hold in asymptotical setups. That means with a lot of observations. And when focusing on only one season for one player, as we did in the Robert Lewandowski's example, we are closer to a low sample setup. Finally, my last point will be that conclusions cannot be solely taken by looking at one metric, of course. You need to use multiple metrics, but also you need to combine looking at these metrics with expert knowledge of the game to have a holistic view of the player, the club, performance. With that said, I hope that you now better understand XG, what they are, and that you will use them correctly. You can also quickly build your own XG model now and potentially do a much better job than me in this video. If you like the video, please let me know in the comment section below, hit the like button and share it to your teammates. And if you want to join the Data Football Club, please subscribe and click on the bell icon so you won't miss any content on this channel. See you soon for another video where football's the game and data's the goal. Bye bye!